Hi, we're going to have a look at something that's really important. I'll bring it up a lot. So even though this is a short video, every time I hit this subject, I'll try to come back to it in the problem and show you how these laws of Isaac Newton all come together. Isaac Newton was a true genius. He co-invented calculus with Leibniz. When you study calculus, you'll be using Leibniz's version because Newton didn't make it for you to use. He made it for him to use to prove Kepler's laws of gravitation, now known as Newton's laws of gravity. And they've stood the test of time until 1915 or so, when modern physics starts, and that's when Einstein, Dirac, Bohr, Schrödinger came up with modern physics, the E equals mc squared side of physics, where we look at the particle and wave duality of things like photons, and we see relativity come into being. Relativity never occurred to people pre that time period. In Newton's period, no one ever traveled in anything close to the speed of light, and funny things happen when you travel close to the speed of light. So for now, we're looking at old-time, regular, classical physics. And Newton had three laws, and they are, and I want to define this word inertia. Because of inertia, which is really mass, the heft of something, because of inertia, an object at rest stays at rest, or an object that moves at constant velocity will keep moving at that same constant velocity unless a force acts on them. What is a force? It's a push or a pull. That's all there is to it. I pull something, I exert a force on it. I push something, I exert a force on it. When I exert a force on an object at rest, it will move. How will it move? It will accelerate. Or if I put the right net force in, it will move at constant velocity. If an object is moving and I want to stop it, what do I have to do? Apply a force to it, according to Newton's first law. Newton's second law is the only equation in the bunch. My wife happens to know this equation.
F equals ma.
Right, F equals ma. The net force is the mass times the acceleration, where acceleration can be delta velocity over delta time. And the third law is for every action, there's an opposite but equal reaction. So, isometrics are based on that. I pull with this arm, I pull equal and opposite with this arm. Nothing moves, but I'm tensing muscles in my arm. Nothing's moving, but I'm pushing my hands together. If I pushed more with this hand, hands would move that way. If I push with this hand more than the other, it'll move the other way. So what's important from this? That Newton had three laws. The one that you have to memorize as one of the equations you have to know is F equals ma. And you have to remember that objects do what they do until you act upon them with a force. And everything you do has an opposite but equal reaction. I push on the board lightly, and the board pushes back. Otherwise, if you went up to an object and pushed on it, you'd go right through it, or it would throw you away. And that doesn't happen. We don't see that happen, so we know that 3 is true by observation. So we're going to take this, and we're going to look at forces. What's interesting about a force is it's tied to an acceleration, and we have seen acceleration as one of the 5 unknowns in the Big Four. And therefore, if we can find the Big Four equations of motion and use them, and we need acceleration, we can find it by getting the force, the net force. And it's net because if I push and pull on an object with the same force, there's no net force. The object won't move because this push and this push are equal, but opposite. So there's no movement. The velocity, which is 0, stays the same. So we'll keep coming back to this when we do problems, and I'll mention Newton's laws. And so keep this short lecture in mind because you may want to review it from time to time as we get into examples and do more problems.